Instead of having multiple processes, you can have multiple threads within one process. They do not have parent-child relationships, but instead all have peer relationships. The context switches between threads are much faster than between processes. These threads still share code, address space, heap, global variables, and kernel context. However, they have their own program counter, thread context, registers, stack, and thread ID. Also, the cost of creating and destroying multiple threads is about half that of multiple processes. However, the context switches are about the same. Within this pool of peers, they can murder each other, but they can also terminate on their own.
pthread tid essentially creates a place for the new thread to live. pthread create is how you create new threads in a pthread program. For example, int pthread create and ampersand tid null func star f void star arg. The first argument, ampersand tid, puts the thread ID into the address of the new thread. The second argument, null, can change attributes of the new thread. This argument is null for the default attributes. Func star f is the thread routine, so it's what the new thread goes to do. And void star arg is the argument to the thread routine. pthread join essentially reaps the threads. For example, pthread join tid null, where tid is the name of the thread that is being reaped. pthread self returns the ID of a calling thread. pthread cancel, pthread exit, and exit are all ways of terminating one or more threads.
This is a graph showing two threads' paths through life from the time they split. These Greek letters represent arbitrary instructions. A single process will do one instruction, then another, switching back and forth in an often unpredictable order. I think it's an important note that the path going through the center and the path finishing one thread and then the other take the same amount of time. It's because as long as you only have one running at a time, it often doesn't save you very much time. The diagonal lines represent when the two threads complete an instruction simultaneously. This is true parallelism. When you can have both threads working at the same time, the overall code progresses up to twice as fast. This, of course, is most prominent when you have multiple cores, because each thread needs its own registers and things. Using multiple threads instead of multiple processes has many advantages, such as their being able to access the same global variables. However, this is also one of their downfalls. One of the cases where this is problematic is if both threads load, update, and then store at the same time. This creates what are known as critical sections.
In order to protect ourselves from these critical sections, we use something called mutual exclusions. These synchronize access to shared variables. pthread mutex lock will put a lock on one thread, so it will wait until it is unlocked to continue. A mutex is a specific kind of semaphore that is only ever 0 or 1. Semaphores can be greater than 1, allowing for more than one thread to be going at once, like if you have many threads but want to limit it to only a few going at once in a particular section. However, we will usually still only use 0 or 1. For semaphores, we usually use PS for locking and VS for unlocking. If the global variable S is 0, the code is indicating a nearby critical section and is not ready for another thread. Once we are clear of it, S gets incremented and the next process can go on its way.
You can picture this like airport security at a small airport. Multiple people can be putting their stuff in bins at the same time. But there is only one X-ray machine, so only one person can be in it at a time.
If only one person could go through the entire process at a time, many people would miss their flight. This would then cause the airlines to lose money. Pipeline queues allow the overall program to run much faster. Let's say you have to go through 6 stages where each is a critical section. We could use a pipeline. This means that while no 2 processes are in the same box at the same time, you can still have multiple processes going at the same time. This increases throughput, or lambda, which is calculated by n processes completing the pipeline per seconds. Latency is the time it takes one process to get through all the colors. In actuality, these stages are usually not the same size. If we were to put a register in between each stage, this would give a latency of 15 clock cycles on either side of each stage. Because only one process can be in each section at a time, the time will take the longest section per process finishing. It will take 570 clock cycles for a specific process to finish, but one will finish every 95 clock cycles. So this really only helps if you have multiple processes or threads. Putting registers in between every 2 sections in this case is unnecessary. If you were to clump the orange and yellow together, this clump will take 80 clock cycles and will still be smaller than the largest at 95, giving it a throughput of 95. If we wanted only 3 registers instead of 4, this would be the most efficient way, with the throughput being 120. Having 2 registers would be 125 clock cycles per section, and having 1 register would be a throughput of 165.